Hi everyone, and thanks for joining me for tutorial 4. In this tutorial, we're going to review multiple linear regression, including how to decide whether or not to add or drop a variable from a model. We'll also expand on interaction or effect modification, and discuss some frequently asked questions on multiple linear regression. And finally, we're going to review multiple linear regression model building with a practice analysis using the HERS dataset. This is just a quick check-in about where you should be at in terms of your understanding of the course material by the end of today's session. So you should understand when to use linear regression and the different approaches or goals for regression models. You should also know how to interpret output, including the intercept and estimates of slopes for continuous and categorical x variables in both simple and multiple linear regression models. You should also be able to calculate a predicted y for a given set of x variables based on your model and know how to interpret estimates with an interaction term in the model. At this point, you should also have an understanding of what confounders and effect modifiers are, including theoretically and how to identify these statistically, and how to decide when to keep or drop variables from a model. You should be able to run a test like the partial f-test or AIC to see which model is better, how to check the assumptions for linear regression, and methods for addressing violated assumptions. So let's quickly recap how to check for confounding. Remember that it should always make sense conceptually that a variable could be a confounder. For example, it's plausible that gender could be a confounder in the association between smoking and FEV because women likely have lower FEV than men on average, and because men may be more likely to smoke than women. And it wouldn't make sense for gender to be on the causal pathway between smoking and FEV because smoking can't affect your gender. So if we think that a variable could theoretically confound an association, we could first look at the bivariable associations to see if our theories about the relationship between the confounder and x and y hold up. But we then want to add the potential confounder to our model and look at the change in the estimate for our primary explanatory variable. And as a rule of thumb, we've said that a change in beta 1 by more than 10% means a variable can be considered a confounder, as long as this makes sense theoretically. So let's return to our example with the dataset that we've worked with over the past few weeks. And in this case, we're checking to see if gender is a confounder for the relationship between smoking and FEV. And we talked about how this could make sense theoretically for gender to meet the criteria for a confounder. When we add gender to our model, we look at how the beta for smoking changes with the addition of gender, because we're interested in the relationship between smoking and FEV. If we calculate the change in beta 1, so 0.21 minus 0.15 divided by 0.21, this equals 0.29. So we can see that our estimate of beta 1 changed by about 29%. So it looks like gender is a confounder, and this makes sense theoretically and statistically. So we should keep gender in our regression model. But what if we added gender to our model and our beta 1 didn't change by more than 10%? Then we would look at the standard error associated with beta 1 to see if it's a predictor or collinear. So we've said that if there's a large increase in the standard error of beta 1, then the variables are collinear. So we should remove this variable from the model. If there's no change in beta 1 but the standard error decreases, this suggests that x2 is a predictor of the outcome. So if a variable is a predictor, should we keep it in the model? Remember that this depends. There are a couple of reasons that we might want to include a predictor. The first is that including this predictor results in a more precise estimate of the relationship between your explanatory variable of interest and the outcome. We might also want to keep a variable for face value. So if gender or age were a predictor but not a confounder, we might still want to keep this. But we don't want to do this for every variable that meets our definition of a predictor, because if we keep too many variables in our model, this results in overfitting your model, which I've said actually gives you less precise estimates and reduces the generalizability of your findings. So if a variable meets the criteria of being a predictor but not a confounder in an assignment, you need to justify why you've decided to keep it in your model or leave it out. Either choice is acceptable as long as you clearly justify your decision. As I mentioned, you should also compare the model fits with a partial f-test or AICBIC to see which is better. The partial f-test tells us if we can add or drop an x variable from the model without increasing the sum of squared error. So this is different from the f-statistic that is included in our output when we run a regression model. So just as a side, the f-statistic in your output for a regression model tests the null hypothesis that all betas equal 0, versus the alternative hypothesis that at least one beta does not equal 0. The f-statistic in your output tells you how the model fits. It's the ratio of explained to unexplained variation in the model. It basically answers the question, is our model better than nothing? Does at least one beta not equal 0? So it's really not all that informative. On the other hand, the partial f-test compares nested models. So it compares a reduced to a full model. For example, a model with only smoke is nested within a model with smoke and age. With the partial f-test, you are essentially comparing the sum of squared errors of the two models. Does the full model have a significantly lower sum of squared error than the reduced model? Does this full model explain more variation than the reduced? As a rough guide, when we conduct a partial f-test, if we get an f-statistic over 4, we can reject the null hypothesis. Here's an example output. Since the p-value associated with the f-statistic is less than 0.05, we can reject the null hypothesis that there's no difference between the sum of squared errors of the models and conclude that we have evidence to suggest that the full model is better. The full model explains significantly more variation than the reduced model. If we find that a variable does not meet the criteria for a confounder, but that the model that includes this variable is better, as shown by the partial f-test, this suggests that the variable is another significant predictor of the outcome. And if this variable does meet the criteria for a confounder, and the model that includes this variable is better, as demonstrated by a partial f-test, this provides further reason to include this variable in a model, because the model that includes it has greater predictive power. The second method for comparing models is to use the AIC or BIC. These measure how well a model fits and penalize for more explanatory variables. The main advantage is that the models can be nested, but do not necessarily have to be nested. It can compare models with entirely different sets of x's. So for example, you could compare a categorical weight variable with a continuous weight variable. The model with the lower AIC or BIC is a better model, because AIC and BIC are measures of unexplained variation. So a lower value means the model fits better. Like with the partial f-test, if we add a variable to a model and find that this model has a lower AIC or BIC than the one without it, this suggests that this variable is a predictor of the outcome. And if it does meet the criteria of a confounder, a lower AIC or BIC provides an additional reason to keep it in the model, because the model fit is better. So as a recap, whenever you're asked if you should include a variable in your model, you should examine the change in beta 1 and the standard error to see if the variable is a confounder, predictor, or collinear. And you should conduct a partial f-test or compare the AIC-BIC of the full and reduced models to determine if the model that includes the additional variable fits better. So this week I got an email from someone in the class who asked about p-values associated with explanatory variables in our model, and if we should look at these in deciding whether or not to include a variable in a model. The short answer is no. As we already talked about, we are looking at the change in beta 1, so the slope associated with our explanatory variable of interest, and its related standard error. But that being said, we do want to look at the p-value for our explanatory variable of interest whenever we're asked to interpret the relationship between this variable and the outcome. This will help us to determine whether or not the relationship between x and y is significant after adjusting for confounders. So if we were asked to interpret the association between smoking and FEV in this example, we would look at our p-value associated with smoking and see that our p-value is less than 0.05. Therefore, we reject the null hypothesis that there's no association between smoking and FEV, and our interpretation of beta 1 would be that smokers have an FEV that's an average of 0.15 liters lower than non-smokers, adjusting for age and gender. Another question that came up this week was whether or not a variable can be considered both a confounder and an effect modifier. And the answer is yes. For example, when we just compared a model that included gender versus one that didn't, we saw that it met our statistical and theoretical criteria for a confounder. But when we fit a model that included a smoke times gender interaction term at the end of the last tutorial, we concluded that the effect of smoking is modified by gender, which also makes sense theoretically. If this is the case, that you conclude that a variable is an effect modifier, you should always report the effect of the primary explanatory variable of interest stratified by the levels of the effect modifier. So in this example, we need to report the effect of smoking among men and the effect of smoking among women separately. If Z, which is gender in this case, is found to interact with X1, which is smoking in this case, we need to look at specific subgroups of Z to make statements about X1. So anything we say about the effect of smoking has to be gender specific. We need to report the effect of smoking separately for men and women. Okay, so let's turn to an example using the HERS dataset. This data comes from a clinical trial of hormone replacement therapy for the prevention of recurring heart attack and death. Data was collected at baseline from 2,763 postmenopausal women with existing CHD. Our research question is there a relationship between exercise and blood glucose? So step 1 is to identify your research question. And this includes the model goal, primary X, primary Y, and other variables that might be important. How are each of your variables measured or coded, and which do you think are important and why? So we're interested in the relationship between a single X and Y variable, so this is an effect size or comparative model. Our primary explanatory variable of interest is exercise, which is a binary variable. And our primary outcome is blood glucose, which is a continuous variable. So linear regression is appropriate to use here. And there are lots of variables in the dataset that could be potentially important to adjust for in our model. So we're interested in the relationship between exercise and blood glucose. So why don't we just include all available X variables in our model? Let's try fitting a model with all of these variables to see what happens. So this is some of the output from the model with everything in it. As you can see, this is a big mess. Where do you even start? How would you interpret the estimates? This would be really complicated. So even though you think that all variables could be important, it's important to have an analytic plan for building your model. Remember, including all X's is bad. This won't predict well on new data, it can lead to overfitting, and it complicates interpretations. There's no right way to fit a model, but there are wrong ways. We need to have a systematic, thoughtful way to analyze our data. There is no purely statistical solution, so deciding which model you use is not just number crunching to get the final model. There are automated model selection procedures that select explanatory variables statistically, including forward, backward, and stepwise selection. These are based strictly on numbers, but usually are not the best approach. We need to think through our model selection theoretically and statistically, and make decisions based on what you think is important and what the data is telling you is important. For the purposes of today's tutorial, we're going to focus on 4 variables that could affect the association between exercise and blood glucose. So once we've determined our research question, the next step is to learn more about the distribution of your variables. And it can surprise you sometimes how variables are distributed. So I was conducting an analysis recently on life satisfaction, with a scale ranging from very dissatisfied to very satisfied. But close to 90% of participants said that they were either satisfied or very satisfied. So the distribution was highly skewed. And so this changed how I interpreted the associations with this and other variables, and ultimately how I decided to measure this variable. So I converted it to a binary variable. You should also check out the bivariable relationships between variables and the primary explanatory and outcome variables. This gives you a good idea about how variables might be related. So do your theories about potential confounders hold up with the data? So is a variable associated with both the explanatory and outcome variable? So what about collinearity? For example, in this data set, there are numerous variables measuring body composition, like BMI, WHR, etc. But you don't want to put these all in your model if they're conceptually measuring the same thing. You might want to check out how strongly these are associated to see if they're collinear, and then see how each of these is associated with the primary explanatory variable and the outcome. This might help you to determine which one to go with if they're collinear. So you might want to go with the one that's more recognizable, like BMI, or maybe WHR is actually a better measure of body composition, so you'll go with that. But these are just examples. But the more important thing to remember is to explore relationships and any hypotheses you might have at the bivariable level before proceeding to multivariable analyses. So based on our bivariable analyses, we have a good idea about the relationship between our variables. So diabetes and smoking are both significantly associated with both exercise and blood glucose. And alcohol is marginally associated with exercise and significantly associated with blood glucose. So this suggests that these three variables could be confounding the association between exercise and blood glucose, as long as this makes sense conceptually. So our next step is to fit our initial model. As I mentioned, we can start with all variables that we think are important and try removing, or we can start with a simple linear regression model and build up. And then we want to determine if we should include each variable in our model and follow the other steps shown here. So let's start with a simple model that only includes exercise. Our intercept would be interpreted as those who don't exercise have a mean blood glucose level of 114.6. The slope for exercise would be interpreted as exercisers have a blood glucose that's an average of 9 milligrams per deciliter lower than those who don't exercise. So now let's try adding age to our model. Do you think age is a confounder? Based on our output, it doesn't look like it. The exercise slope doesn't change much. The standard error does decrease slightly, suggesting that age might be another predictor. But it doesn't decrease by that much. So how can we test if the model is a better fit by adding age? We can either conduct a partial F-test or examine the difference in AIC or BIC between the models. But here we'll conduct the partial F-test. So we can see that the model that includes age is significantly better. It explains significantly more variation in the outcome than the previous model. So should we keep it in our model? I'm going to say yes. It's not a confounder, but we often adjust for age in health research for face validity, because it's often such an important determinant of health. Also, the significant partial F-test indicates that age is a significant predictor. So let's keep it in the model because doing so will increase the precision of our estimate of exercise. Remember that we're mostly interested in the estimate for exercise, our primary explanatory variable, but the interpretations for the intercept and for the slope for age are shown here. So next, let's try adding alcohol to our model. This doesn't change our estimate for exercise much compared to the last model, and when we looked at our bivariable relationships earlier, alcohol wasn't strongly associated with both X and Y, so it's not a confounder statistically. But if we conduct a partial F-test, which isn't shown here, the test is significant, suggesting that the model is better. Remember, better means smaller error, so the predicted values are closer to the observed values, meaning that our model has significantly better predictive power. This is more important for predictive models. It's not as important with an effect size model. And we don't want to keep everything in the model, we need to be selective. Remember, including all X's is bad because it can result in overfitting and won't predict well on new data. Including more X's increases our R squared, but if less important X's are added to the model, this can make our model unstable. Our slopes are then bad estimates and won't predict well with new data. So you could argue to keep alcohol in using the same logic as age with our last model, but because I don't think it's all that important for face value, I'm going to leave it out. There's quite a large change in the exercise estimate with the addition of smoking into the model. This suggests that smoking is a confounder, so we should keep it in the model to adjust for it. This will give us a less biased estimate of the association between exercise and glucose. We can also conduct a partial F-test. The results of this aren't shown here, but this is significant, providing more evidence to keep smoking in the model as it will improve precision of the estimate of the exercise effect. So next, let's take a look at diabetes. Is it a confounder? There's a really big change in the exercise slope, so this could suggest that it's a confounder. But if we think through this theoretically, could diabetes be on the causal pathway? It's possible, so exercise could help to prevent or delay diabetes, and diabetes of course affects glucose levels, so it might not be appropriate to adjust for this as a confounder. But maybe diabetes is an effect modifier, so the effect of exercise on glucose depends on whether or not you have diabetes. Remember from our discussion last week that there are two ways to check for effect modification. You can use stratified models, so fit a multivariable model for each level of the effect modifier, so one for diabetics and one for non-diabetics. And this works well for categorical variables, which is what we have here with our diabetes variable. And the second option is to add an interaction term. This works well with continuous effect modifiers, but interpretation is more difficult. So let's try both methods. Here are models stratified by whether or not participants have diabetes. So we run separate models for people with and without diabetes. Among non-diabetics, exercisers have a mean blood glucose level that is 5.4 units lower than non-exercisers, controlling for age and smoking. But among diabetics, there's no significant difference between exercisers and non-exercisers with respect to blood glucose levels, controlling for age and smoking. So the effect of exercise on blood glucose depends on whether or not participants have diabetes. Having diabetes modifies the effect that exercise has on blood glucose. Exercise has an effect on glucose levels among non-diabetics, but the effect is not significant among diabetics. What about a model with an interaction term? Remember, last week we talked about how we need to use a partial F-test to check if the interaction term is significant. The results of this test are shown in the box at the bottom of the slide. Since the p-value associated with the F statistic is less than 0.05, we can reject the null hypothesis that there's no difference between the models and conclude that we have evidence to suggest that the full model that includes the interaction term between exercise and diabetes explains significantly more variation than the reduced model that does not include the interaction term. What this means is that allowing the effect of exercise to vary according to whether or not you have diabetes fits the data better than not allowing it to do so. This tells us that we have evidence to believe that the effect of exercise on glucose depends on whether or not you have diabetes. Diabetes appears to be an effect modifier for the association between exercise and glucose. So how does the effect of exercise differ between diabetics and non-diabetics? Using the same process that we discussed last week, we can estimate the effect of exercise for diabetics and non-diabetics by inserting a 1 into the full regression equation for diabetics and 0 for non-diabetics. Among non-diabetics, this effect is simply the estimate for exercise, negative 5.47. Among diabetics, we add the estimates for exercise and the interaction term, which gives us an estimate of negative 0.14. We would interpret this as, among non-diabetics, exercisers have a mean blood glucose that is 5.5 units lower than non-exercisers, adjusting for age and smoking. Among diabetics, there is a non-significant difference of 0.14 units in mean blood glucose between exercisers and non-exercisers, adjusting for age and smoking. So why are the results here slightly different compared to when we fit stratified models? Recall that with stratified models, exercisers had a mean blood glucose that was 5.4 units lower than non-exercisers, adjusting for age and smoking, while there was a non-significant difference of 0.11 units in mean blood glucose between exercisers and non-exercisers. The reason why the results are a little bit different with the interaction term is that this model with the interaction term treats all variables except for exercise as equal for diabetics and non-diabetics, while the stratified models allow all coefficients, including the intercept, to differ between the two groups. So the effects of age or smoking as confounders are averaged for diabetics and non-diabetics in a model with an interaction term, whereas in stratified models, the effect of these variables are allowed to differ for diabetics and non-diabetics. So both approaches are acceptable, but this is why the results of the two approaches don't always give exactly the same results. Here are some simplified formulas to help learn how to calculate the effect of exercise for diabetics and non-diabetics. This is just another way of looking at what we just calculated. So this doesn't include the confounders age and smoke, just to keep things simple. But hopefully this is helpful to some of you to look over if you want to see how the effects on the previous slide were calculated. Remember that you should always have some conceptual or theoretical reason for including a variable in your model as a confounder or effect modifier. If it doesn't make sense conceptually, you shouldn't include it in your model. Once you've decided on a final model based on adding and dropping variables, checking the model fit, and so on, you should then check your model assumptions. Just as a brief reminder, independence is checked through knowledge of study design, normality is checked using a QQ plot, and we use a residual plot to check linearity and equal variance. Remember, these assumptions don't have to be perfectly met, only approximately met. So what if your assumptions are violated? Again, we talked about this last week, so I won't spend too much time on this, but if the relationship is nonlinear, you could transform x or y to make it more linear, but usually we transform x. So you could take the log of x or the square root of x, but this does complicate interpretations. You could also use polynomial regression, where you include both x and x squared in your model, and this will allow you to fit a quadratic or parabolic shape. Another way to address nonlinearity is to categorize a continuous variable. After you transform your variable, you can then check your diagnostic plots to see if the issue is addressed. Or you can also look at the AIC or BIC value. The model with the smallest AIC or BIC is a better model. If variance is not constant, we usually transform y. Usually you'll want to log y or take the square root of y. Again, this does complicate interpretations though. In the next tutorial, we'll introduce logistic regression using sample data from the Western Collaborative Group study. We'll also go over how to interpret logistic regression output and calculate odds ratios with categorical and continuous variables, and how to estimate the log odds of an outcome.
Thanks for watching our video. Stick around, guys, because we got lots more.